Okay, so we have talked about the radius, we have talked about how to estimate using gravitational collapse condition, how to estimate the size of nucleons, number of baryons in a neutron star, right? We have also talked about what will be the size of the neutron star and all that. Now today we are going to talk about the composition of neutron star. So basically what I want you to ask me is that, sir, why are you calling this a neutron star at all? Why not nucleon star or something else? Why neutron star, the name? Now to get an idea or to get an answer to this question, let us use a very approximate crude model where we will consider the neutron star to be an ideal gas of degenerate electron, proton and neutron. Now you see, at such high densities neutrons are essentially free. But if we have a free neutron over here, right at this moment, here, what will happen? It will decay. Lifetime around 10 minutes or so, it will just decay. Why? The reason is that the reason for the decay of free neutron here is that it will decay to proton and electron and what? Yet another neutrino, right? Now the thing is that antineutrino. The thing is that right now if there is a neutron on my hand, it will decay. Why? The reason is that because of Pauli's principle. Again, you will ask me how. The reason is when the neutron's mass is more than proton, right? So the neutron can decay to proton and electron. But what is more important to ask is that, are there free quantum states available for the proton and electron to go? Of course, they are available right now over here. So the neutron can decay. But in this case over here, normal beta decay is prohibited because, again, due to Pauli's principle. Because at this moment there is no free available states for the proton and electron to occupy inside the neutron star. As a result, normal beta decay will not happen. So you can say neutrons cannot decay over there. Neutrons cannot decay because even if they decay, where will the protons and electrons go? There are no available states. Now the same argument we can say differently is that neutrons cannot decay if the Fermi energy of neutron is less than the Fermi energy, sum of the Fermi energy of proton and electron. So the same type of argument we are giving. Now here, let us consider, since the mass of electron is much less compared to proton and neutron, it will be very relativistic. So EF of electron is basically PF into E, and same for what about the EF for neutron? This is mass of neutron mn c square plus PF n whole square divided by twice mass of n. Same for proton. Now what is the value of PF? The value of PF is 3n by 8 by root into the density n. Okay, so they will not decay if this condition is there. Now let us consider the equilibrium condition. So equilibrium condition is that this is equal to EFn is equal to EFP plus EFE. Okay. Now if we put all these factors, whatever is there, if you put all these factors over there, then you can solve this equation considering the fact that mass of neutron minus mass of proton is of the order of 1.3 MeV. But you will need a value of density. So let me give you this value. So for densities of the order of 2.5 into 30 kg per meter cube, you can check yourself. It has to be done numerically, putting in all the values, that we get the number of neutron to proton of the order of 200. So this means that as long as there is one proton and one electron for every 200 neutrons, neutrons will not decay. So you see there are so many neutrons compared to electrons and protons, and they will not decay. And so the neutron star is entirely supported by the neutron degeneracy pressure. And this is the reason, since there are one proton, one neutron for every 200 neutrons, so this is the reason why we say that this is basically a neutron star and not a nucleon star. Okay? And remember this thing, who is causing this? Who is causing this thing? Nn by Np of the order of 200, it is not the strong interaction. Who is responsible? It is basically gravity. So gravitational, right? Gravitational force is responsible for the neutron star itself, along with the degeneracy pressure by the neutron star. Remember this, it is not the strong interaction which is causing this thing, but in fact gravitational.